Hello, so today we'll be discussing the hints to assignment number 5. I'll be discussing problem number 4.22, 4.28 and 4.37. So the first problem is 4.22 and this is a cylinder which is placed in a constant electric field. This is the top view of the cylinder. So there's a constant electric field E naught and the cylinder has a susceptibility chi E. So this will be our x direction, y direction, and so if r is along this direction, r cap, then phi will be this angle. So you have your electric field E naught, which is E naught in x cap direction. Therefore, rho b, which is the this leads to a polarization in the dielectric cylinder, and we are supposed to calculate the electric field inside, which is some E. So rho b will, as we know, is divergence of P. Which in this case will be 0 because the polarization is constant, and the surface charge density, the bound surface charge density is P dot r cap, which is P cos phi. Okay, so this leads to an induced electric field EI, which is given by minus P by 2 epsilon naught, and so the total electric field inside the cylinder will be E naught plus EI. So if you do this, then use the right formula for polarization P, then you will find the total electric field inside the dielectric cylinder. One can also do this in an iterative way. So you have a constant electric field E naught, which gives rise to a polarization P naught, which is given by epsilon naught chi E E naught. So this in turn gives rise to a bound surface density sigma B0, which is epsilon naught chi E E naught cos phi. This surface charge density in turn induces another electric field E1, which is minus chi E E naught by 2. So this gives rise to polarization again. So this is given by chi E epsilon naught E1 this time, and this is equal to minus epsilon naught chi E square E naught by 2. So one can go on to continue this. So this will again give rise to a surface charge density sigma B1, which is given by minus epsilon naught chi E square E naught cos phi by 4. And when one considers all the infinite iterations and do the infinite sum, will obtain the net electric field. So this is about 4.22. Now problem number 4.28 consists of two metallic tubes which are coaxial, and these are placed in a container which contains dielectric oil. And the inner cylinder inner tube is maintained at a potential V and the outer one is grounded. So we are supposed to find the height up to which the oil rises in the space between these two tubes. So this is the h we are supposed to find. Suppose we take this to be y and the total length of the tube to be L. Then we know that the capacitance per unit length of such a coaxial tubes is given by lambda, where lambda is the charge density, 2 pi epsilon naught k ln b by a, where a is the radius of the inner cylinder and b is the radius of the outer cylinder. So interestingly, this can now be considered as two capacitors which are in parallel, C1 and C2, and C1 is the capacitance up to the length up to which the oil is filled in between the tubes, and C2 is the capacitance of the tubes where there is only air. So the total capacitance therefore will be given by Ky plus L minus 1. So once we have the capacitance, we know that the energy stored in the capacitor is half Cv square. Therefore, the energy will be given by pi epsilon naught ln b by a Ky plus L minus y v square. Once we have the energy stored and its dependence on y, we can calculate the force on the dielectric, which is just dE by dy at constant V. So this has to be equated to the weight of the water, weight of the oil, the dielectric oil. So that is given by V square minus A square. So once you equate these two, you can find the height up to which the oil rises in between the two tubes. Okay. So this is the hint to problem number 4.28. So now problem 4.37, which is the fifth problem in the assignment. So this has a dielectric sphere with dipole P, which is along z direction at the center of the sphere. Okay. So this gives rise to an electric field, as we all know that the electric field produced by the dipole is given by this. But as the dipole is placed inside a dielectric, this induces a polarization of the form R cube, where P1 will be also along z cap direction. So this in turn induces surface charge density, the bound surface charge density, which is given by P dot r cap, which in this case can be calculated to be 2p1 cos phi by 4 pi r cube, where r is the radius of the sphere. So the net polarization now will be, because of the bound surface charge density, there will be an electric field inside the sphere, and that in turn induces polarization P naught, P2 along z direction. So the total polarization P will now be P0, which I just described, plus a new polarization because of this bound surface charge density, and this P2 will of course be constant along z cap direction. So this gives rise to a volume bound charge density, which is minus del dot P which in this case will be 3p1 dot r cap minus p1 by 4 pi r cube. As p2 is constant, the divergence on p2 will be 0. Okay. So now this volume bound charge density can be interpreted in a interesting way. So if you have a dipole which is giving rise to some electric field, which gives rise to an electric field 3p1 dot r cap, 3p dot r cap minus p by 4 pi epsilon naught r cube, then this can in turn be treated as if there is a free charge density which is equal to del dot, right. So this is from the Gauss's law. So these two configurations are equivalent, the free charge density of minus epsilon del dot E or the electric field due to a dipole. So therefore in this case rho b is of this form. So this can be treated as if this is equivalent to having a dipole minus p1 z cap. Therefore we have the electric field which is equal to E0 plus, because of this new dipole we will have a net electric field E0 plus E1, which will be given by 3 p minus p1 dot r cap in r cap direction minus p1 divided by 4 pi p minus p1 4 pi r cube epsilon. Okay. So but now the bound charge density has changed, because the bound charge density is now given by 2p1 cos theta, which is due to p0 by 4 pi r cube plus p2 cos theta. So therefore this in turn induces an electric field which is minus 1 over 3 epsilon 2p1 by 4 pi r cube plus p2 along z cap direction. Therefore the net electric field now will be E0 plus E1 plus E2, and this must be equal to, so the net polarization must be equal to chi E epsilon naught E net. So once one does this, one will find the P1 and P2 which are required to find the net electric field, and from that one can find the potential inside and outside the sphere.
Let's continue with the same assignment from problem number 4.39. So here what you are having a conducting sphere maintained at the potential V naught, embedded in a medium of susceptibility chi e. So what we are supposed to find first of all is the potential at anywhere in the space. So obviously I should be solving this Laplace equation, which will satisfy the boundary condition V at R equal to R equal V naught, and if you consider this as your Z axis, then the other boundary condition would be Z equal 0 plus should be equal to V at Z equal 0 minus. Okay, so there can be only one unique solution for this, which is nothing but VR equal to V naught R by R, where R here is radius of the sphere. Okay, now next thing is let's find out the free surface charge density on the sphere. So the formula will be sigma f, which is nothing but n cap dot the displacement vector, which needs to be evaluated at the surface of the sphere. So this will be nothing but epsilon naught k, which is dielectric constant, del V del R, okay, evaluated at the surface. So for this, in the upper hemisphere, this will be nothing but sigma f epsilon naught V naught by R, and here it will be sigma naught k V naught over R. So similarly, the electric field for this potential is, we can use this formula to evaluate it. Let's come to the polarization. Here P is nothing but I naught, okay, electric field E. And if you calculate the bound charge density, first of all rho B will be nothing but minus divergence of P. Here everywhere it will be 0. And sigma B, which is nothing P dot n cap, it will be 0 for z greater than 0, and this one for z less than 0. Now if we calculate the net sigma, I will be getting rho B plus rho F. What you will find is, if you calculate it for, let's say for z less than 0, sigma net would be nothing but epsilon naught V naught by R to K minus chi E, which is nothing but same as the net charge density on the upper hemisphere. Now, so in the next part of the problem, we are supposed to argue that for this particular symmetry or geometry, whether I can use that same potential or not. There are, first of all, that potential V R that we just got before, this should satisfy all the necessary boundary conditions. Now if we consider this potential, if we construct an equipotential surface here, and we should be able to say that the potential at Z plus should be equal to the potential at Z minus, which will not be the case if you consider this particular VR. So physically, if we want to argue is that now this particular potential will induce a bound charge on this surface, which will alter the potential itself. So we cannot have this for this configuration. Now the next thing is, so what if we have this configuration? In the same medium of the same susceptibility. Here what happened is, first of all, we will satisfy is continuous all across all boundaries. And if you see exactly here, you will find out at this surface we will not be able to produce the bound charge sigma, since I will have n dot r cap dot, let's say you can say p equals 0. So let's move to the next problem, which is nothing but problem number 4.40 in the book. So the geometry of this problem is nothing but you have a wire of linear charge density lambda. Now, and you also have a tiny sphere of radius r placed at a distance s from the wire. So one can write down, so first of all let's discuss about how do I do that. See, the field that would be produced by the wire will be in this direction. Since I consider the sphere to be very tiny, I can consider the field due to this wire to be uniform. So let's write down E external. Let's say we know this due to the wire. Let's say E external S cap. Now, if you would like to find out the field inside the sphere, it would be nothing but E external divided by 1 plus the susceptibility of the sphere divided by 3. Please refer example 4.7 for this. Now the net force due to the wire on the sphere, I can write it will be P dot E external d tau. Now P in this case would be nothing but epsilon naught chi E into E. Okay, then if we substitute this into this equation, then we can find out the net force experienced by that tiny sphere. So let's continue with the next problem. The next problem is problem number 5.5. Okay, in the first case, I have a wire of radius A. Where I have current I which flows through it. So the surface charge, the surface current density here in this case will be nothing but 2 pi A. This is a straightforward kind of things. Say this is part number A, part number B. In part number B, what you are having is you are having a current density, volume current density, which goes as 1 over S, where is S can be this. Okay, now Js, let's write down this way, J naught by S. Now if you would like to find out that current that we say before, this will be nothing but Js 2 pi S ds. Obviously from 0 to A. This integration will be nothing but 2 pi A J naught, which will give me J naught equal I divided by 2 pi A. So that means therefore I can write Js nothing but I divided by 2 pi As. Okay, so let's go to the next problem, which is problem number 5.6. So here also, first of all, I have a phonograph, a circular disc phonograph recorder. Okay, and this is rotating about its axis with an angular frequency omega. Now, and it also has a current a surface charge density sigma. So if you consider as a ring of infinitesimal, an infinitesimal ring here, dr, which is at a distance r, let's say from the origin, I would say. So the current through this ring is nothing but 2 pi r dr sigma omega by 2 pi. Now this would in turn give me the current density, which is k di by dr, which will be nothing but sigma omega r. As simple as this. So this is part number A. And in part B, what the geometry of the problem is, you have a sphere, and the sphere is rotating about this z axis, let's say, with angular frequency omega. What you need to find is, you need to find the current density at any point r, theta and phi. So let's use this straightforward formula, rho velocity v, and here in this case I will have omega cross r. Now, which I will be getting this one, since I have omega along z axis. Okay. Now this specifically, if you want to calculate this is very quite easy, because I can write this like sine cos phi x cap plus sin theta sin phi y cap plus cos theta z cap, which is nothing but sin theta, if you evaluate cos sin theta phi cap. So I would be having J to be nothing but rho omega r into sine theta phi cap.
Hi, this is Paramita and I am going to give you some hints for 5.7, 5.12 and 5.15. Let us start with problem number 5.7. In problem number 5.7, you are asked to prove that there is a current and charge confined in a volume, say nu, and you have to prove this, where P is the dipole moment and J is volume current density. So to solve this problem, let us start with the RHS, which is the rate of change of this dipole moment, and you know that dipole moment can be written as q times r, which is integral over rho d tau r. D tau is the elementary volume. So now I can write the RHS dp dt as del rho del t r d tau, and using the continuity equation, you can now write del rho del t as minus of divergence of J. So I replace this by minus divergence J r d tau over a volume. Now using this, I can also write that divergence of xj is equal to x divergence of j plus j dot grad x. Now when you solve this, you will find out jx, and when you solve this, you will get that if I take the volume integral, this will give me a surface integral, and as the charge is confined within the volume, say nu, I know that the j dot ds, where s is the surface, it would be 0. So when you use that in here, you will find out the relationship between jx d tau and the left hand side, and using that equation, whatever you obtain here, you can now find out that taking all the components, say jx, jy and jz, you can find out that j d tau is basically dp dt. So use this hint and prove it. Now let us move on to the second problem, which is 5.12. In this problem, you have to use the solution that you have obtained in example 5.6, and using that example solution, you can find out the magnetic field at the center of a spherical shell which has surface charge sigma and having a radius r. Let us now try to solve this problem, how to find out the magnetic field at the center. So please recall what we have learned in example 5.6 in Griffith's book. We found out the magnetic field at a point, say P, at height z above the center of the circular loop. And then how we did that? We took a line element here, say dl prime, and we find out the component of magnetic field along the z direction, if this is the z direction. And you also have seen that the horizontal components actually cancels. So whatever I have is the component along the z axis, and that gives me the value of magnetic field at a point, say P, above this circular loop, which is given by mu 0 I r square by 2 r square plus z square to the power 3 by 2, where this is this distance between the dl prime and the point, and z is this height. Now we will use this in finding the magnetic field at a center of a spherical shell. How will I do it? Let us just see how we can implement this idea in finding the magnetic field. If we can take a circular ring at an angle theta from the center, where r is the radius and this circular ring has a width say d theta. So, I can immediately see that the radius of this circular loop, let me draw this again. So, this is the spherical shell and I want to find out the magnetic field at the center. So, I am taking a circular ring of width d theta at an angle theta with respect to the z axis, and this is the radius. So, this is theta. So, I can immediately see that the radius of this ring is r sin theta and it is at a height r cosine theta from the center. So, now we already have found out what is the magnetic field of a circular ring at a height z from the center of the ring. Now, if I replace that z by r cos theta, because r cos theta is now the height of the center where I want to find out the magnetic field, and if I now replace r by r sin theta, because r sin theta is the radius of the circular ring which I have chosen to find out the magnetic field. So, in the expression of B which I found out in example 5.6 in Griffith, I will replace r by r sin theta square and denominator will be r sin theta square plus z square. Z is now r cos theta. So, r square cos square theta and whole to the power 3 by 2. So, now if I compute it, I get mu 0 I r square sin square theta divided by 2 r cube. So, basically I am getting here mu 0 I by 2 r sin square theta. So, this is for a single ring like this at an angle theta with respect to the z axis. So, I call it dB. Now, this is due to the current in this ring. So, I will call this dI. Now, what is dI? dI is k r d theta, because you know that k is the surface current density, which is the current per unit length perpendicular to the flow. So, I can write dI as k r d theta. Let us now write k as sigma v. Here the spherical shell is spinning with an angular velocity omega. So, and it having a charge density sigma. So, I can immediately write k equal to sigma v. So, q by 4 pi r square, and v is omega cross r. So, I write omega r sin theta in place of v. So, I know sigma, I know v, I write k as this. So, k comes out to be q omega sin theta divided by 4 pi r. Now, using this value of k in the expression for dI, I get dI equal to q omega sin theta by 4 pi r and then r d theta. So, r will cancel and I get q omega sin theta d theta divided by 4 pi. So, this is for the elementary current that is there in this ring. So, let us now use this in the expression for the dB that I have here. So, dB is the magnetic field at the center due to this one ring at an angle theta. So, now let us write dB. dB is equal to mu 0 by 2 sine square theta, and then I write the value of k that I obtained. So, I get omega q sine theta by 4 pi r d theta. This is the di. So, this is giving me mu 0 by 8 pi r q omega sine cube theta d theta. Now, we have to be very careful about taking the limit of theta. You can see here that the magnetic field that we have, the expression that we have now, the dB, which is due to this ring at angle theta. So, if you take the limit of theta from 0 to pi by 2, so then you consider all such rings between the center and the upper half. So, basically you are integrating over all such rings. So, now you take theta equal to 0 to pi by 2 and you consider all such ring and you add the contribution of all such rings to the magnetic field. But there are rings in the lower half. So, if you take that into account, you have to take the limit of theta to be 0 to pi. So, when you take the limit of theta from 0 to pi, you consider all such ring that is contributing to the magnetic field at the center. So, when I integrate this, it will give me the magnetic field at the center of the spherical shell. This is how we implement the idea of example 5.6, where we learned how to find the magnetic field at a height z above the circular loop to find out the magnetic field at the center of a spherical shell. Now, we move on to problem number 5.15. In problem 5.15, you are given a thick slab which is extending in the x and y direction. So, this is x, this is y, this is z, and you have a infinite slab of width 2a. So, basically you are having infinite slab like this. So, this is plus a, this is minus a. So, please recall from example 5.8 in Griffith's book, we have learned how to find out the magnetic field outside and inside a infinite slab. Magnetic field inside the slab. So, let us draw the slab again. So, this is plus a, this is minus a, this is my y axis, this is x and this is z. So, to find the magnetic field inside, let us take a Amperian loop inside this slab at height z minus z. So, basically we are having a loop here, and now we will use the Biot-Savart law, and which gives us closed integral of B dot dl is mu 0 I enclosed. Now, you see that the direction of B is negative in this direction and positive in this direction. So, when you use that and find out B dot dl in the whole loop, you will get mu 0 times and I enclosed in terms of j. So, when you do that, you find out B inside for z less than equal to plus minus a. So, this is how we do this. Now, to get the magnetic field outside the slab, you will be taking Amperian loop again, and in that case you will find out closed integral of B dot dl will be mu 0 times the total I enclosed, and which will again give you B outside. So, this is for z greater than equal to a and z greater than equal to minus a. So, you get two expressions for B outside. So, solve this using the Biot-Savart law. And you can also see by symmetry that Bz will be B minus Z. Once you find out B as a function of height Z, then you can plot B as a function of Z, and you get a plot which will show you that how B changes with Z. With this, we finish the hint for assignment number 5. Thank you.